Okay, we're going to finish up our discussion of classical statistical mechanics by making use of the maximum Boltzmann distribution that we just derived to calculate a useful quantity. And specifically, what we want to think about, as I mentioned last time, is collision between molecules in a dilute gas. Dilute gas because that's usually the simplest circumstance that we can think about. The molecules are not interacting unless they come into intimate contact and touch. And when they touch, they bounce off of each other or they collide, change momenta, and so on. And so we imagine a dilute gas as a kind of collection of classical, almost billiard ball like molecules that are all bouncing against each other, moving with some speed, colliding, bouncing off, and changing momentum and changing their direction of travel. And this is what the gas roughly looks like if we don't worry about kind of fine details of quantum mechanical nature and so on. And so the question that we want to ask ourselves is how often do molecules collide, or what is the rate of molecular collisions when the gas is under some temperature and when the gas molecules are as of a specific mass? What is the average rate of collisions in a sense? Very roughly speaking, to do this, to get a very accurate estimate, one needs to do a lot of mathematical work, and ultimately the answer that one arrives at is not very different from doing a very coarse estimate. And so we're after a very coarse estimate, a very rough sense for what determines how often or the rate of molecular collisions. And so with that in mind, let us focus our attention on this kind of a problem. And so this is going to look a little bit weird, but let us walk through this. What I have in mind is, again, a dilute gas of molecules where the molecules are hard spheres or billiard balls, right? They have a hard exterior where they can't penetrate each other. If they touch, they collide and they bounce off of each other. We are going to train our attention on some specific particle that we're going to call our test particle that I've labeled with these hash marks over here. And we're going to imagine our particle is traveling through space over some amount of time. Let's suppose we watch our molecule travel in space over some time delta t. So particle travels for some, let's say, short time duration delta t. As it travels, it sweeps out what is called a collision cylinder. What do we mean by this? As this particle, which has some specific diameter, travels forward, with how many molecules in this scenario will it collide? In this very fictitious scenario where I've placed other molecules in the gas at these positions. As this molecule travels forward, and given that it's a hard sphere, anytime it touches a molecule, it collides. With how many molecules will this particle touch effectively or collide as it moves forward? Well, as it goes forward, it's very clear that it's going to collide with this molecule. It's clear that it's going to collide with this molecule. It'll just miss this molecule. And here the molecules will graze each other. They will touch, which we count as a collision. And so all of these molecules would collide as this molecule travels forward. This molecule would be missed, would not be collided with. What's the condition for colliding or not colliding? Well, we can see that the center of the particle has to be in this cylinder that I've drawn. And if the center is in this cylinder, or just on the border of the cylinder, there will be a collision. If the center is outside of the cylinder, there will not be a collision. What is this cylinder? We speak of this collision cylinder being swept out as this molecule moves in space. What is the length or cross-sectional length of this cylinder? It is equal to twice the diameter of the particle. So here's the diameter of the particle. Now above this, there is a distance equal to the radius. And above, and a distance equal to the radius below. And so the total distance here, or the cross-sectional length of this collision cylinder, is equal to twice the diameter. Diameter plus the radius, which is twice the diameter. The cross-sectional area swept out by the cylinder that determines whether molecules in principle collide with this test particle or not is equal to cross-sectional area of the cylinder, cross-sectional area of the collision cylinder is the area of the circle, which is pi times the radius of the circle. But the radius of the circle is not r, but it's d. It is the diameter of the particle, or radius plus radius. So that's the diameter also. And so the cross-sectional area of the cylinder is pi d squared. And we're going to define the symbol sigma. The symbol sigma we're going to call the collision cross-section for obvious reasons. Collision cross-section. And the term collision cross-section is actually quite important in physical chemistry generally. It gets applied much more broadly than the simple molecular collision model that we're using. And so the collision, the cross-section, once again, is pi d squared. What is the distance that the particle covers when it moves a length of time delta t? Distance, let's say, traversed by particle in time interval delta t is equal to the speed with which the particle moves times delta t, right? Distance is speed times time. So if the particle moves for a time delta t, the speed that it, or the, I'm sorry, the distance that it covers is the speed with which it moves times delta t. But we know that particles move generally with different speeds. And we're after a rough estimate, some average rate of collisions. And so instead of using some specific speed, we should use the average speed of the molecule. And so this is the average speed of the molecule as determined from the Maxwell-Boltzmann distribution that we just talked about times the time delta t. So let us go back to the question that we wanted to ask. In this kind of a circumstance, if this is our test particle, with how many particles will this test particle collide in a time delta t as it moves through the gas? How should we think about this? Well, we know that if the molecular center falls in the cylinder, the molecule will collide. And so the question is, how many particles do we expect to find in the cylinder? Well, the number of particles that are in the cylinder with which our test particle can collide, roughly speaking, is equal to the number density of molecules in the gas, which is some property of the gas, right? If the gas is under a certain temperature, under a certain pressure, or is containing a certain volume, and there are a certain number of particles, then the number density, the number of particles per unit volume, will be determined by things like the pressure and the temperature. If we know the density of the gas, the number density, and we know the volume of this collision cylinder, that allows us to calculate the number of molecules that we expect to find within this collision cylinder. And if we're saying that every molecule, roughly speaking, that is found itself on average in this collision cylinder will undergo a collision with our test particle, then the number of particles in the cylinder, which will be the number of collisions in this time delta t, roughly speaking, the number of particles in the collision cylinder that will collide, so the number, I want to make sure I'm not blocking, the number of particles in the collision cylinder that can collide, or let's say will collide, with our test particle is the gas number density times the volume of the collision cylinder. Right? So density times volume gives you the number of particles. Remember that the mass density times volume gives you the total mass. The number density times volume gives you the total number of particles. And so number of particles in collision cylinder will look like the density, N over V, times the volume of the collision cylinder. Well, what's the volume of the collision cylinder? The volume of the collision cylinder is the cross-sectional area of the cylinder times the length of the cylinder. Let us remind ourselves, what is the length of the cylinder? It is the distance that the particle travels when it travels for a time delta t. The distance that it covers is the average speed times delta t. So the volume of the collision cylinder is the cross-sectional area, which is pi d squared, times the average speed times the time interval for which the particle travels. This is, very roughly speaking, the number of collisions that the particle will suffer or undergo in a time delta t, whatever delta t might be. That number of collisions that the particle will undergo depends on what the density of the gas is. The larger the density, the more collisions there will be, which makes sense. If the gas is concentrated, it will have a large number density. There will be many guys in this collision cylinder. If the gas is very dilute, this will be small. There will be few guys in the collision cylinder as our test particle sees it. The diameter of our particle, when viewed as a hard sphere, right? So molecules are not spheres, first of all. But roughly speaking, if you take a molecule of some complicated shape and you approximately draw a sphere that covers it, and then determine the diameter of that sphere, this is what that d would be. And given that it's a coarse estimate, this is good enough for now. The number of collisions will be larger the larger the diameter of the particle. And that makes sense. The analogy is appropriate for you moving through a busy intersection, at least before COVID times. If you are going straight like this, you will suffer a relatively small number of collisions with other people. But if you stick your arms out and you walk like this, you will collide with more people. Makes sense. And so the larger the molecular diameter, the more collisions there will be. So big guys collide more frequently for all the other parameters fixed. The faster you're moving, the more collisions you'll suffer. Why? Because you will cover a larger length. And over the same unit of time, you will have expectedly more collisions. And of course, the longer you travel, the more collisions you expect to undergo in total. So this is the total number of collisions that the particle will undergo as it travels for this amount of time. But this amount of time is arbitrary. What is more appropriate to ask about is what is the rate of molecular collisions? Or, said in other words, what is the frequency of molecular collisions? The rate or the frequency of molecular collisions is the number of collisions that occur in that unit of time divided by the unit of time. And so all that's going to happen is the delta t will disappear. So let's rewrite that. The rate of collisions that our test particle will undergo per unit time, right? Rate of collisions, rate of molecular collisions of our test particle. In other words, the number of collisions per unit time, is equal to the number of collisions in time delta t divided by the interval of time delta t. And so this thing looks like the density the collision cross-section pi d squared, or sigma, times the average speed. So this is the rate of molecular collisions that a test particle will undergo. Oftentimes this is given, or at least in Engel and Reed, this is given the letter, oops, I don't know what happened there, little z 1, 2. Struggling with my z here and dropping things. Z12. Oh, man, I really want to make this small, because the big Z is used for something else. Z12 meaning that particle 1 collides with some other particle 2, or some other particles 2. We're not saying that our test particle is the same as all the other particles, but certainly we are trying to imply this in a dilute gas of the same kind. What is the average velocity? Well, we know what the average velocity is, or I'm sorry, the average speed, I should say, not the average velocity. And so the single molecule collision rate, if you write down what the average speed is in terms of temperature and mass, looks like N over V, the collision cross-section sigma, which is pi d squared, times 8 kBt over pi m to the 1/2 power. So that's the single particle collision rate. It depends on the density of the gas. The more dense, the faster the collision rate, or the larger the collision rate. It depends on the molecular cross-section, or the cross-sectional area, pi d squared, where d is the molecular diameter. It depends on the temperature. The larger the temperature, the larger the collision rate, because the speed is larger, the average speed. And it depends inversely on the mass, because the average speed depends inversely on the mass. Although keep in mind that the collision cross-section, the size will also generally change with mass. So there's one thing that has to be corrected here to make this more accurate. Of course, again, we're being very coarse here, but one thing that we did not account for, among many other things, but one very obvious thing that can be easy to correct, is the fact that other molecules, as this molecule is moving forward, are not stationary. They're also moving. And so what matters is the relative speed with which molecules are moving. If this molecule is also moving, then one needs to consider the fact that both of them are moving and consider how quickly molecules are approaching each other, given that they're both moving. What that does is replace the average speed here by the average relative speed. And the net effect of this is to change m, the mass of the particle, by the reduced mass. So if this is particle 1, and these are all particles 2, and so this has mass m1, this has mass m2, that if we account for relative speed, or account for relative motion of the particles with respect to each other, so account for relative motion relative particle motion, the net result is to change Z12 by a factor of the reduced mass as opposed to the mass itself. Collision cross section, 8 kBt over pi mu, where mu is the reduced mass, to the 1/2 power, where mu is m1, m2, m1 plus m2. And if particles 1 and particles 2 are the same and have the same mass, the result will be to replace m by m over 2. The reduced mass of identical particles is m over 2, the mass of any one particle divided by 2. And so that's the collision cross section, or I'm sorry, the collision rate. And in the notes, I estimate for you just how many collisions a molecule can be expected to undergo, moving with a reasonable speed and having a reasonable density. And the rate is actually quite large. The answer is about, I believe, 1 billion collisions per second, roughly speaking. For the rate of collisions. You're seeing whether the numbers line up. Okay. So now that we have the collision rate for a single molecule, it might also be of interest to ask, what is the total rate of collisions per unit time? How many total collisions are there, or what is the total rate of collisions? Well, remember that to answer this question, remember that the test particle that we chose was no more special than any other particle. We could have chosen any one other particle. And so the total rate of collisions should be accounted for by asking how many collisions, roughly speaking, each particle is going to undergo. Well, each particle is going to have this kind of a collision rate. How many particles are there of this kind? There are n of them. And so one defines the total collision rate, and usually it's defined per unit volume, and you'll see why it's per unit volume. This quantity is usually given the letter big Z, and this looks like, make sure I get this right, 1/2 n over v, and I'll explain why I'm writing it like this, n over v sigma 8 kBt pi mu to the 1/2 power. Compared to the single particle collision rate, there is an additional factor of n over v. Why n over v? Well, first of all, why n? Because there are n of these kinds of molecules, and each molecule is undergoing collisions at this rate. So the total collision rate is n times the collision rate of a single molecule. The division by v just makes it be kind of a factor of square of the density. And so the units of this is the number of collisions per unit time. So the units of this is per second, second to the 1/2 power. The units of this is per second per unit volume, because there's an additional factor of volume that's been divided here. The factor of 1/2 is so that we don't overcount the number of collisions. When we say that each particle is going to undergo collisions with all the other particles, and there are n of these kinds of particles, we are overcounting the number of collisions because we are counting the collision of this particle with that particle differently from the collision of, or we're counting that differently from, sorry, let me say that again. We are saying that the collision of particle 1 with particle 2 is a different thing than the collision of particle 2 with particle 1. But there's just one collision between particle 1 and 2. And so by multiplying the collision rate by n, we are overcounting by a factor of 2 because we're viewing each collision from both sides, whereas it should be viewed just once. And so by dividing by 2, we correct for our overcounting. And so this is the total collision rate. It goes as the square of the density. The density occurs twice, first in the individual single molecule collision rate, and then in the collision rate for all the molecules, and so on. And so that's the total collision rate. Now, there's a very useful quantity that is derived from the collision rate, and that is as follows. That is the collision time, or the time between collisions. What do we mean by this? We mean that as molecules collide at some point in time, they will bounce off of each other, and then the next instance in time, they will continue traveling before they collide again. And suppose there's another molecule here that is on a collision course with this molecule, and so this molecule will travel some time, let's call it tau. Well, let's call this delta t. Sometime delta t, I'm going to define as letter tau, called the collision time, or the time between, or sorry, I shouldn't say the time, the average time between successive collisions. Successive collisions. So it is the time on average that the particle travels uninterrupted before it gets hit again by somebody else. So this is the time between collisions. How do we calculate this time? Well, the rate, or the time between collisions is 1 divided by the rate of collisions. This is the same idea that one encounters in vibrational motion. There's this idea of a vibrational frequency and the vibrational period. The vibrational frequency is how many vibrations per unit time or per second. The vibrational period is how long between successive vibrations or the motions back and forth. And so this is the same idea. The frequency of collisions is how many collisions per unit time. The inverse of that is the time between a single collision, or the time between a single collision that takes place. From time 0, which is the end of some collisions, time 0, up to the next collision. That's the time that the molecule travels uninterrupted or before it collides. And that's 1 divided by the rate of collisions, or the collision rate. So this is, for a single molecule, this is 1 over this z, little z12. So this is tau, the time between collisions. How long or how far does the molecule travel before it hits somebody else between collisions? If the molecule travels at time tau on average between collisions, what distance does it cover if the temperature is T and the mass of the particle is m? Well, the distance that the particle covers, distance or average distance, actually I shouldn't say average, it's already average by design. Distance covered in time tau, or the distance the molecule travels between successive collisions, is defined as the symbol L, little l, and this is called the mean free path, or the average distance that the particle travels while free or uninterrupted or between collisions. This quantity is just the average speed with which the molecule travels times the average time that the particle travels between collisions. So the mean free path is related to the average speed and the time between collisions, or the collision time, the average collision time. What is this quantity, the mean free path? The mean free path will then be equal to, let's write it out in its full glory. The mean free path will be equal to the average speed times tau, which is the average speed divided by the collision rate, the single particle collision rate, right? These are related as one over the other. The collision time, tau, is equal to 1 over everybody that used to be in the collision rate, the number density, now in the denominator, times the collision cross-section, times the average speed, a kBt over pi m. I'm sorry, not pi m, pi mu, the reduced mass, to the 1/2 power. In my notes, I have this as m, and I have a square root of 2. The reason for that is that if you have particles of the same kind, mu is m over 2. You have a root, you have a 1 over 2 under the square root sign, and then that gets flipped, and so there's a factor of square root of 2 that should come out. And so that's the collision time, and so this leads to the mean free path. Therefore, the mean free path is the average speed times what? This was also the average speed, right? And so the average speed should cancel the average speed. And the end result is 1 over, if the particles are the same kind, I'll include the square root of 2, times the density, n over v, times the collision cross-section. This is for all same molecules in the gas. If the collisions are all between identical molecules, so it's not a gas mixture. The density of a gas, particularly if it's an ideal gas, can be related to the pressure and the temperature, right? We know that P, if this is the pressure, right, not the momentum, I apologize, PV equals number of particles times kBt. As we've seen in class, this is identical to PV equals nRT, or N over V equals P over kBt. And so similarly, this can be replaced. N over V can be replaced. And the answer is right, so if we're dividing by N over V, the kBt goes in the numerator, P goes in the denominator, kBt over P times 1 over square root sigma. That's the collision rate, where sigma, once again, is pi times the molecular diameter squared, the collision cross-section. And so on the notes, I tell you that for an argon atom at room temperature and atmospheric pressure, the mean free path is about 80 nanometers. You can also rewrite this in terms of molar quantities. If you don't want to work with Boltzmann's constant, you can write this in terms of the gas constant R, and write this as RT. But now you're going to have to include the Avogadro number in the denominator to make everything work out, times 1 over square root of 2 sigma. So that's the mean free path. And this formally concludes our relatively quick, but necessarily so, introduction to classical statistical mechanics. And now we're fully in the domain of chemical kinetics as we go forward.